In previous videos, we showed you the decentralized object, the decentralized function, and the decentralized database with 3 types of storage. Today, these concepts are put together to demonstrate the possibility of building a decentralized compiler. Think about the Ethereum virtual machine opcodes. If you would sort them by their code, you will find out that there are empty ranges, like here, where you can add additional opcodes. This is how the layout looks like. And one empty opcode space can be filled by a regular 1-byte opcode like add, mul, sub, div, or an entire class of 2-byte opcodes. And we call this an extended opcode. So from 126 free opcode positions, we get 32,256 possible extensions, an extended Ethereum virtual machine, or EEVM. Since the participant functions should be built by multiple parties, we cannot build this compiler alone and only pretend to be decentralized, so we propose that we build together a decentralized compiler. So how would these functions be stored and executed? And I have a short demonstration. This is an IDE for our Taylor EVM language with a compiler, deployer, and debugger. This code defines 2 functions, add2, which adds 2 inputs A and B, and mul2, which multiplies 2 inputs A and B. Both of them put one result on the stack, C. Using the exposelib function, we encode these function definitions for deployment within a storage contract. Check our previous video about our decentralized database. There we demonstrated a very gas-efficient way to store immutable data on-chain by including it in the contract bytecode. Functions for a decentralized compiler must be immutable, so this storage method is exactly what we need. And this is the functions data that will be deployed as part of a contract bytecode. We do a factory deploy, which means this data is sent to a factory contract which adds some behavior bytecode to this non-executable data. This additional behavior bytecode will in turn make our functions executable. And we make the transaction. And we have our deployed contract. Start with an address starting with 3DA0. And if we look at the receipt and at the logs, we see that the second topic is this address. So let's take it and go to ringb with etherscan and check the contract bytecode. And this is our data. And the rest is the runtime bytecode that will be executed. And now we can call each function, but for now we need to encode each argument manually. So we will do this here. The first argument is the function index. We will put 0 and try out the add2 function. And the next arguments are the function inputs, 4 and 5. So we are now adding 4 and 5. And let's go through the debugger so we can see what's happening. And the result is 9. Now let's try the mul2 function at index 1. And the result is 20. in hex format. Okay, so we have deployed a contract that defines some functions that can be executable. But these functions contain metadata about them and documentation in the same bytecode in a compact format. So now we can take this address of the deployed contract and register it in an Ethereum data service contract. And we will register it as a set of data. So we are going to insert another set at position 7, which we will name dCompiler functions. And we have two functions. Each function record is 2 slots. Actually, this is 2 slots, and it is of type 13. We have 6 fields and a key length of 2. And as salt, we will put our contract address. In the future, this entire process will be automated. So I'm taking the address, extending it to 32 bytes, and we'll add something else. We'll add this data offset on the last 2 bytes, and also the records count. So now we'll take this and use it as a salt. And now we define the fields of the records. And we actually have to put the salt here. So we'll take it again. And then make the transaction to add the set. And we can already see it here. So let's see what it contains. And we can see the two functions add2 and mul2, each with 2 inputs and 1 output. And this is the offset at which the bytecode of each function exists in the deployed contract bytecode. The functions in this set are ready to become extended opcodes in a decentralized compiler. And we are waiting for your proposals for such EVM extensions. Maybe we will include those in the demo of compiling itself. What you saw here is that the proposed functions are saved on-chain as an EDS library. The present implementation works with the Taylor language for the EVM, and the system can be used as an interpreter too. And everybody is free to construct their own specialized language, both compiled or interpreted. The decentralized compiler system has tight integration with the Ethereum data service and dtype DB.